Okay, so in this second lecture, I will give you the idea about the local stability and global stability with the context of very simple problem. And then in next couple of lectures, when I will be introducing the ordinary differential equation models for population dynamics, then we are going to apply this result for practical models and then understand the behavior of the system. And if time permits in this lecture, towards the end I will give you some idea about the bifurcation. That means when one of the eigenvalues that you are asking in during my last lecture, that if any one of the eigenvalues becoming 0, then what is going to happen in the system. Now for stability, there are different types of concept, that is stability of an equilibrium, stability of a solution, stability of two nearby trajectories and so on. So in this lecture I am concentrating only with the stability of equilibrium point. Now of course, first of all I need to define what is an equilibrium point, and then I will be explaining you that how a given nonlinear system can be linearized around a equilibrium point and study their stability behavior. And not in this lecture, but afterwards when I will be considering some practical problems from population dynamics, then I will explain that why this kind of linear stability is important. But briefly I can mention here that most of the nonlinear system that we are having or we are dealing with, those are very complicated, and most of the time you cannot find out any explicit solution, and till today there is no way to find out a general solution for a nonlinear ordinary differential equations. So first of all, let us define what is a equilibrium point for a single variable system. So single variable system is defined by dx dt equal to fx. Sometimes I will be considering this type of equation by introducing a parameter also. So that means some parameters will be involved with this system, because in case of bifurcation we are interested to study that how the system's behavior is dependent upon the particular magnitude or values of the parameters, or some interrelation of the parameters involved with the model system. So this is the most general form. Alternatively, we can write down this system as dx dt, that is equal to f of x comma alpha. So x is the dependent variable, t is the independent variable, and alpha is the parameter. Now for the time being we are not concentrating on this equation, rather we can concentrate on this particular equation, because if I want to define the equilibrium in terms of this equation, that will be quite complicated for you at the initial stage. So for this system, what is an equilibrium point? Equilibrium point means it is a rest point. So if you start from here, trajectory will not move from this particular location. So that means velocity of x is 0 when x takes that particular value which is labeled as equilibrium. Then we can call x equal to x star is an equilibrium if and only if f of x star this is equal to 0. This is 0 means once your x equal to x star, then your dx dt equal to 0. So therefore x star is an equilibrium point or rest point. Now you need to keep in mind that why we are interested for equilibrium point. We are interested for equilibrium point only for the reason because equilibrium point is itself a solution of the given system. Why? Because this is a nonlinear equation. For most of the nonlinear equation you cannot find out the general solution. For some of them we can manage a solution, but you can easily verify that if x equal to x star satisfies this condition, then xt given by this constant value x star is a solution for this equation, because fx star is by definition is equal to 0 and derivative of x star with respect to t is 0, it satisfies the equation. So therefore it is an equilibrium point, and sometimes it is also called an equilibrium solution for the given system. Now before going to mathematical definition of stability of an equilibrium point and how to judge the stability of a nonlinear system by method of linearization, I just want to give you a very simple example, and from geometry you can understand that how we can determine the stability of the equilibrium point. The given system is, for the time being we can consider dx dt this is equal to x square minus 1. So your fx is given by x square minus 1. So if you want to find out the equilibrium point, so that means some x star satisfying this condition, that means we need to solve the equation x square minus 1 equal to 0. So this gives you x equal to plus minus 1, and in terms of our notation x star, we can write x1 star equal to 1 and x2 star, this is equal to minus 1. So these two are equilibrium points. Now what are the stability concept of the equilibrium points? The answer is that if you give a small perturbation from the equilibrium point, then whether the solution trajectories has a tendency to come back to the equilibrium point or not. So in case of single variable problem, x is on x axis with the advancement of time. So you can give perturbation around the equilibrium point, so that means you can give perturbation such that the point moves either on the right hand side of the equilibrium point or on left hand side of the equilibrium point. In other words, if we start from a nearby point of the equilibrium, then the solution trajectory will be approaching towards the equilibrium or not. If solution trajectory is from both sides approaching towards the equilibrium point, then we can call it as a stable equilibrium. If not, then it is unstable. Why I am saying if not? It may happen for certain system, it may happen that you have an equilibrium point. If you start from a point on the right hand side of the equilibrium, solution will be approaching towards the equilibrium. But if you start from a point on the left hand side of it, it may start diverging from the equilibrium point. In that case, although from one side it is approaching towards equilibrium, but from other side it is diverging from the equilibrium. So therefore, in combination we can say this is unstable, because stable means from all the directions solution trajectory should be approaching towards the equilibrium point. Now for this system, just looking at the property of increasing function and decreasing function in terms of derivative, we can judge the stability of these two equilibrium points. You just try to understand how it is possible. So first of all, we consider this graph. This is x direction and this is x dot direction, right? In x dot plane, if you draw this curve x square minus 1, so this will be a parabola like this, correct? So this is your point x1 star, this is equal to 1, this is this one, and this is your point x2 star, this is equal to minus 1. Now you consider a point x0 at this position, that is point is on the right hand side of the equilibrium, that is x1 star equal to 1. So this x0 satisfies the condition, that is x0 greater than 1. If your x0 is greater than 1 and if you substitute this x0 here, right, so what is the sign of dx dt? If your x0 greater than 1, then x dot is also greater than 1, correct? So therefore what we can conclude that xt, this is an increasing function of t, right? So from which point you are starting, xt will be taking the values greater than the initial values. So therefore if you start from a point like this, solution trajectories will be having a tendency to go away from this equilibrium point, right? Similarly, you can choose an initial point, maybe here, right? So consider this is x10, this is x20. Now just remember, in this case both x10 and x20, they satisfy this restriction because they are belonging to -1 to +1. So whenever x10 and x20 belongs to this range, just for simplicity we are assuming that these can be combined as that is any x0 lies between -1 and 1, then your x dot, sorry, this should be greater than 0, not greater than 1. if your x0 satisfies this condition, then from here you can find x dot less than 0. So once x dot less than 0, so then you will be having xt is decreasing, right. Once xt is decreasing, so on this part you will be having direction of the solution trajectories towards this way, right. So finally we are left with the situation that is your x0 is here. So in the third case, what you are having, your x0 is less than minus 1. So whenever your x0 is less than minus 1, so therefore x square minus 1 is positive. So therefore x dot, this is greater than 0, and therefore xt is increasing, and therefore you will be having the direction of the solution trajectories towards this way. Now if you look at this equilibrium, x1 star equal to 1, if you start from some nearby point as the initial conditions, solution trajectories are diverging from this equilibrium, correct. So therefore this equilibrium is unstable, and on the other side this is your equilibrium point, and if you start from some nearby point, therefore solution trajectories will be approaching towards the equilibrium point x2 star equal to minus 1. So therefore from geometry, this x2 star equal to minus 1, this is stable, and x1 star, this is unstable, right. Now you should keep in mind that these properties are actually called local stability property. Why this is called local stability property? Because if you look at this equation, then dx dt equal to x square minus 1, this is defined for all real values of x, right. But for this case, x2 star equal to minus 1, we cannot make a general statement that for whatever may be your initial condition from where if you start, solution trajectory will be approaching towards the equilibrium point x2 star equal to minus 1. We cannot say that, because in between there is one more equilibrium point x1 star equal to 1. So that means for any initial conditions, solution trajectory will be approaching to minus 1 if and only if your initial value x0 is less than 1. So that means it is a local property. Although the given problem is defined over the entire real line, but this property is valid only within this domain. Similarly, if you start from some point here, it will be converging to this equilibrium point x2 star equal to minus 1. It don't have any capability to cross this equilibrium and decide whether it will be approaching to this point or not. So therefore this stability is local property, this instability is also a local property. Local in the sense, this property, that solution trajectory diverging from this equilibrium, that is x1 star equal to 1, this is valid only for your initial condition chosen as greater than minus 1. It is not for all cases. Now as I have mentioned that most of the time we will not be able to find out the solution explicitly, and sometimes this particular geometric consideration is not possible due to complicated nature of the function involved with the given differential equation. So let us try to understand that how some mathematical technique can be developed in order to understand the local stability property. Now local stability means here what we are going to do, that given system is x dot equal to fx, you know that x equal to x star is an equilibrium point for this system. What we are going to do, we are just interested to give a small perturbation around the equilibrium point x star, and then we are interested to judge that whether this perturbation is going to die out with the advancement of time or it will grow with the advancement of time. If it is approaching to 0, its absolute value is approaching to 0 as t tends to infinity, therefore we can say that solution trajectory xt will be ultimately approaching to x star, and if yt is growing with time, that means either diverging to plus infinity or diverging to minus infinity, so that means xt is moving away from the equilibrium, so then it is called an unstable equilibrium. Now how it can be evaluated from the linear analysis? So we consider a perturbation is given by x star plus yt, where y is a small perturbation, so therefore it satisfies the condition, that is, it is much less than 1, right. Now we are assuming that this is a solution for the given system. So if we substitute this expression into the given equation, so x dot t will be equal to y dot t, right, xt equal to x star plus yt, x star is constant, so therefore x dot t equal to y dot t, and on the right hand side you will be having x star plus yt. Now here we are assuming f is a smooth function, so that means it can be expanded in a Taylor series around the point x star. So if you expand in Taylor series, so you will be having fx star plus f dot x star times yt plus dot dot. So as we have assumed that yt is much less than 1, so therefore we can discard second and higher order of y, and by definition x star is an equilibrium point, so therefore your fx star is equal to 0. So then from this equation, after substituting this and using this approximation with the assumption that yt is much less than 1, you are having this linear equation y dot t is equal to f dot x star times yt. So equivalent to, you can consider this is as alpha yt. And if you just recall from my first lecture, I have already mentioned that modulus yt, this modulus yt will be approaching to 0 if alpha less than 0, right. So if this happens, so therefore we can say that xt will be approaching to x star as t tends to infinity if f dot x star this is less than 0. Why? Because alpha is f dot x star, correct. So this is the conclusion. Similarly, we can say that modulus yt, this is approaching to plus infinity if your alpha greater than 0. So therefore we can say that xt does not converge to x star as t tends to infinity if f dot x star this is greater than 0, right. Now the point is that if your f dot x star is exactly equal to 0, what is going to happen? If your f dot x star is exactly equal to 0, so then this is equal to 0. So therefore solution is yt equal to constant. It is neither converging to 0 nor diverging to plus infinity as t tends to infinity. So therefore we cannot say anything from the linear stability analysis. So in that case what we can do, but that I will not be covering within this lecture, but in that case you can use some Lyapunov function technique in order to judge the stability. But of course I will give you one simple example in this lectures itself in order to understand what is the notion of global stability in terms of single variable problem. So therefore we can conclude that for this simple one variable system, if x dot equal to fx is your given system and you are able to find out x equal to x star is an equilibrium point, so then you can judge the stability of the equilibrium point f dot x dot equal to fx with the equilibrium x star if and only if your f dot x star is not equal to 0, right. So therefore we can say x dot is locally asymptotically stable if f dot x star this is less than 0 and this is unstable if f dot x star this is greater than 0, right. Now if we just apply this technique to the previous example where we have obtained the stability from geometry, We can just check whether these two condition is going to satisfied for that particular system or not. So quickly you can write down this system as x dot equal to x square minus 1. So this implies your fx equal to x square minus 1. So from where you can calculate f dot x equal to 2x, right, and then your f dot x1 star, that is 2, this is greater than 0, right. So as f dot x1 star greater than 0, so therefore x1 star is unstable. We have obtained the same conclusion earlier from geometrical consideration, and similarly f dot x2 star, this is equal to minus 2, this is less than 0, right. So therefore your x2 star is stable, right. So this is the idea for the local asymptotic stability for one variable system. Now the next question is that, okay, in the previous lecture we have learned something about the phase portrait and nature of solutions for two variable system of linear equation. What is the utility of those kind of solutions? The idea is that in two variable nonlinear system you can consider the general format as x dot equal to fxy and y dot, this is equal to gxy. So these are system of two nonlinear coupled ODE, correct. So in this case also you can define that x star comma y star, this is an equilibrium point, this is an equilibrium point whenever your f of x star comma y star, this is equal to 0, is equal to g of x star comma y star, right. Now we are interested to understand that whether this equilibrium point is stable or not. So what we need to do, we need to give some perturbation around this equilibrium defined by xt equal to x star plus ut, yt equal to y star plus vt. As earlier, we can assume that both u and v, they are much less than 1, such that second and higher order can be neglected, right. Now if we substitute these expressions, that is xt equal to this one and yt equal to this one in this particular system, then first of all substituting in first equation, we find that dx dt, that is equal to ddt of x star plus ut, so this is equal to u dot t, this will be equal to f of x star plus u y star plus v. So again we are assuming that f and g, they are both smooth functions. So once you are assuming they are smooth functions, so therefore you can write this is equal to f of x star y star plus del f del x evaluated at x star y star multiplied by u plus del f del y evaluated at x star y star multiplied with v plus dot dot, correct. So what is your f of x star y star? This is an equilibrium point, so this is equal to 0, right. U and v are much less than 1. So therefore this system can be simplified as du dt, that is equal to a11u plus a12v, where a11, that is equal to del f del x evaluated at x star y star, and a12, that is equal to del f del y, that is evaluated at x star y star. So this is the first linear equation. So if you do the same exercise for the equation y dot equal to gxy, so analogically or analogously you can derive that the second linear equation will be dv dt equal to a21u plus a22v such that a21 equal to del g del x, that is x star y star, and a22 that is equal to del g del y, this evaluated at x star y star. Correct. So the idea is that now the equilibrium point x star y star will be locally asymptotically stable if we can derive the condition, or we can ensure that both the perturbation ut and vt will be going to 0 as t tends to infinity. Correct. So therefore, in order to judge the stability of the equilibrium point x star y star for this coupled nonlinear system, we need to understand whether the zero solution of this linear system is stable or not. Correct. Now from the previous lecture what I have covered earlier, you can recall that in all the solutions they are actually of the form that is exponential some constant into t multiplied by a column vector, that is combination of this type of two solution as a general solution for the given system, or you have exponential alpha t multiplied by some trigonometric function as the column vector, or in case of repeated eigenvalue you have e to the power lambda t multiplied with either 1 0 or t comma 1. So you can clearly understand that if both the eigenvalues are negative or both the eigenvalues have negative real part, then your ut and vt will be approaching to 0 as t tends to infinity. So therefore, stability condition for x star y star of this nonlinear system, that means local stability condition, is given by that both the eigenvalues associated with the coefficient matrix given by a11, a12, a21, a22 should have either both real negative eigenvalues or both the eigenvalues with negative real part. Right. Now the question is that how we can judge, or what are the conditions from which we can clearly understand that whether the solutions are stable or not. So question is that whether we need to find out the complete solution. Answer is no. There is a very specific way, or rather simple logic from where you can easily check in case of two variable system whether the zero solution for this linear system is stable or not, and accordingly you can conclude that whether the equilibrium point x star y star for the non-local system, non-linear system is locally asymptotically stable or not. Now for this system we can put it into the compact matrix notation, that is ddt of uv, that is equal to capital A multiplied with the column vector uv, where A is the matrix a11, a12, a21, a22. This is also called Jacobian matrix. Jacobian matrix for the given nonlinear system and evaluated at the equilibrium point x star y star, because all these aij's they are defined by these expressions. So therefore this is partial derivatives with respect to x and y of f and g and evaluated at the point x star comma y star. Now eigenvalues are actually roots of the characteristic equation, that is a minus lambda I2, this determinant, this is equal to 0. If you expand this system, then you will be having lambda square minus a11 plus a22 multiplied with lambda plus a11 a22 minus a12 a21, this is equal to 0. So this is your characteristic equation. Now you can just have a close look to this expression. You can write this equation as lambda square minus trace of a multiplied with lambda plus date of a, this is equal to 0. Correct? Without any loss of generality, you can assume this. And once this is the case, and if you denote trace of A by P and determinant of A by Q, so then this equation can be simply written as P lambda plus Q, this is equal to 0. So once you have this quadratic equation, is roots are given by lambda 1 comma 2, that is equal to P plus minus root over P square minus 4Q divided by 2, correct? P plus minus root over P square minus 4Q by 2. Now what we are looking for? We are looking for the stability of this linear system. So that means we need any one of two conditions should be satisfied. Number 1, either lambda 1 lambda 2 both less than 0, or real part of lambda 1 as well as of real part of lambda 2, both of them is less than 0. This is the requirement for the stability of 0 solution of the linear system, and accordingly local asymptotic stability of equilibrium for the nonlinear system, right? Now if you look at this expression, so there are two possibilities. In this case, that means both the roots are real and negative. This case 1 corresponds to the requirement that P square minus 4Q is greater than 0, which ensures both the roots are real, right? Now how can we ensure that both the roots are negative? We can ensure with this one if we demand that P is also less than 0. Now you just try to understand that P negative, P square minus 4Q is positive. The possibility is that either Q greater than 0 or Q less than 0. Now in this case we can exclude the possibility Q less than 0. Why? Because if Q less than 0, then from this equation you can observe that product of the root is negative, product of two roots is negative, so which clearly implies one root is positive, another root is negative. So that means the requirement both of them negative is already violated, right? Now if we assume that Q greater than 0 with P less than 0 and this condition is satisfied, then we can ensure that equilibrium, that is x star comma y star for the nonlinear system, is locally asymptotically stable. Similarly 0 solution for the linear system is also locally asymptotically stable. Now from this condition how we can ensure both the roots are negative also? This ensures roots are real, your P is negative, Q is greater than 0. So then just try to convince yourself that this quantity, that is root over P square minus 4Q, has the magnitude less than P, because this is P square minus 4Q with Q positive. So therefore this quantity has the magnitude less than P, your P is already negative. So whenever you are adding a quantity with magnitude less than P, then the resulting quantity is negative, and then P minus this quantity is clearly negative, so both the roots are negative. Similarly, you have one more possibility, that is P square minus 4Q, this is less than 0. P square minus 4Q, this is less than 0. If you have this condition that P square minus 4Q is less than 0, then automatically if P less than 0, then it ensures that both the roots are actually complex conjugate with negative real part, because P square minus 4Q less than 0 implies that roots are complex conjugate. So this will give you the imaginary part, and P less than 0 ensures that both the roots are having negative real part, correct? So therefore if we combine these two conditions, then we can say that u comma v equal to 0 comma 0 is stable if p less than 0 and q greater than 0. If any one of these two conditions are violated, then you will be having that equilibrium point which is unstable. Now the question is that in previous lecture I have shown some different types of phase portrait. Now the main question is, all those phase portraits can be related with these two quantities P and Q? Answer is yes. Now I will explain how that can be done in PQ plane. So first of all, you just try to convince yourself this is your P axis, this is your Q axis. With some particular intention, I am not extending the lower part. Why? Because from previous discussion you can recall that whenever Q less than 0, then product lambda 1 lambda 2, this is negative, correct? So therefore what you are having, that means what kind of conclusion you are having about the equilibrium, that both the eigenvalues are of opposite sign, real and with opposite sign, so therefore equilibrium point is a saddle point. So a typical phase portrait in this domain, that is for Q less than 0, you will be having this one. Suppose this is approaching to this direction, this is approaching to this direction, so therefore your phase portrait in this domain will looks like this one or some format which is topologically equivalent to this one. So that means either any one of these two axes will be rotated or stretched depending upon the given coefficients you are having for the system under consideration, right? Now the rest of the part we are left with, that is p square minus 4q less than 0 or p square minus 4q greater than 0. So of course p square minus 4q equal to 0, this is given by this parabola, correct? So once you have this parabolic structure, then you should keep in mind that your equilibrium point, that is 0 comma 0, is stable whenever p less than 0. So on this side it is stable, on that side it is unstable, correct? Now first of all you can convince yourself within this domain, that is inside the parabola, your p square minus 4q is negative, and outside the parabola p square minus 4q is positive, right? How can you convince yourself? Because if you take one point here on the p axis, that is 1 comma 0, so what is p square minus 4q at 1 comma 0? That is 1, which is greater than 0, right? Similarly, if you choose a point inside this domain, that is say 0 comma 1 on q axis, then p square minus 4q is minus 4, so therefore less than 0. Therefore within, that is in the inside of this parabola, your p square minus 4q less than 0, outside it is greater than 0. So here what you are having, that both the roots are complex conjugate with negative real part, right? So it will be spiraling inwards. So if your P and Q lying in this particular domain, you will be having this kind of structure, phase portrait here, right? Similarly, if you have your PQ within this domain, then it will be look like this one, but it is unstable, right? If you come out from the parabola, so within this domain, what are the roots? Both the eigenvalues are negative real numbers. So therefore, a typical format of the phase portrait will looks like this one. So these are approaching towards this 0 0, and here you will be having this kind of structure, this one, this is away from the equilibrium. Now the point is that you should not be confused with these two notations, that here all the time solution trajectories will be having tangent along the vertical axis. No, they may be having solution trajectories that is tangent along horizontal axis, depending upon the fact whether magnitude of lambda 1 is greater than lambda 2 or magnitude of lambda 2 is greater than lambda 1. So either this one or some topological equivalent form like this, and also similarly here. Now what will be the last case? Last case is that we have considered one more thing, that you will be having concentric circles. Where we will be having those kind of concentric circles? We will be having concentric circles on this vertical line. So if you take any PQ on this line, so that means your P equal to 0 and Q is non-zero. Once P equal to 0 and Q is non-zero, and also Q is positive here, above the line Q equal to 0. So therefore you have purely imaginary complex conjugate eigenvalues. So on this axis you will be having phase portrait like this, right. So for a given two variable system, you can linearize around the equilibrium point, then you will be having a system of linear equation. Then you can immediately calculate what is P and what is Q, and depending upon the magnitude of P and Q, you can try to judge where you are for the chosen values of P and Q, and accordingly you can understand how the phase portraits will looks like, right. Now the last point in this kind of relation between solutions for linear system and non-linear system, I will give you a particular example from where you can see that the behavior of the solution for the linear system will be matching with the behavior of the system for the non-linear system, because we are judging the stability of the equilibrium point by using linearization method. There is a important theory that is called Hardman-Grobman theorem. It says that you have an equilibrium for a given non-linear system such that all the eigenvalues of the linearized matrix having non-zero real part. If this condition is satisfied, that all the eigenvalues have non-zero real part, so then solution trajectory of the nonlinear system near the equilibrium point will be topologically equivalent to the structure of the solution trajectory near the trivial equilibrium point for the corresponding linear system. And there are very few examples which are available for which you can convince yourself that okay, this behavior of the solution trajectories for the linear system and non-linear system, they are more or less identical. Now I will give you one specific example from where you can clearly visualize how these two linear and non-linear systems seems to be equivalent near the equilibrium point, and that actually justifies that okay, this kind of theory can be applied for other higher variable system, but of course it is quite difficult to visualize that this kind of one-one correspondence between two systems. Rather we need to depend upon the available theories to understand that okay, or in order to convince ourselves okay, there are some possibility to make a one-one correspondence between the nature of the solutions near equilibrium point for a non-linear system as well as corresponding linearized version. So for that purpose we consider this simple system . We consider this system x dot equal to x plus y square and y dot equal to minus y. So I am considering this system only for the reason because I can show you that although this is a coupled of two coupled nonlinear equation, still you can find out their solution explicitly. So first of all, you just verify that in this case your x star y star is 0, 0. This is the equilibrium point. If we want to match with the previous example, then you can understand that your f of x comma y, this is x plus y square and g of x comma y, this is actually minus y. So therefore, if you calculate the matrix capital A, so therefore del f del x at 0 0, this is 1, del f del y, that is 2y at 0 0, this is 0, then del g del x, this is 0, and del g del y, this is minus 1. Already I have considered this type of problem earlier, correct? So what will be the phase portrait for the linear system, that is u dot equal to u and v dot that is equal to minus v. In this case, phase portrait will looks like this is away from the origin, this is towards origin, and therefore phase portrait will looks like this one. Right. Now how to obtain the solution for the nonlinear system? Y dot equal to minus y, this gives you the solution yt equal to y0 e to the power minus t. Then if you solve the second equation, first equation, that is x dot equal to x plus y0 square e to the power minus 2t, so this will imply that ddt of x e to the power minus t, that is equal to y0 square e to the power minus 3t, right. So therefore by solving this equation you can find x e to the power minus t, that is equal to some constant minus y0 square by 3 e to the power minus 3t. Next, if you assume at t equal to 0, your x equal to x0, so therefore you can find x0 plus y0 square by 3, this is equal to c. Substituting back into this equation, you will be having xt equal to x0 plus y0 square by 3 times e to the power t minus y0 square by 3 e to the power minus 2t. So I am just substituting this value of c here and then multiplying both sides by e to the power t, right. Now once you have this structure, then you can just write down the solutions in this format: y0 square by 3 times e to the power t minus y0 square by 3 e to the power minus 2t, and yt, this is equal to y0 e to the power minus t. Now in this case, first of all, if you choose your initial condition as y0 is equal to 0, if you choose y0 equal to 0, so that means your solution comes out to be xt equal to x0 e to the power t and yt, this is equal to 0. So that means you are starting from a point on x axis and it shows that solution will remain always on x axis, correct, xt equal to x0 e to the power t. So that means as t tends to infinity, solution trajectory will be approaching to either plus infinity or minus infinity along x axis, depending upon whether your x0 is positive or negative. So therefore on x axis you will be having this kind of behavior along this direction if this is your origin, right. So along this line solution will be diverging to plus infinity. Next, if you choose the initial condition in a little bit clever way, that is you choose your initial condition, that is x0 plus y0 square by 3, this is equal to 0. Why I am considering this is equal to 0? Because now I want to see that if is it possible to find out one curve along which solution trajectory will be approaching towards the origin. So in order to do that, I need to consider the coefficient of exponential term having positive factor of t, that coefficient should be equal to 0. So here you have e to the power t, so that's why I am considering x0 plus y0 square by 3 equal to 0. If you consider this one, then what is the structure of your solution? The structure of your solution comes out to be that xt, this is equal to minus y0 square by 3 e to the power minus 2t, and yt, that is equal to y0 e to the power minus t. correct? Now if you eliminate y0 and e to the power minus t from these two equations, then you can verify that you will be having actually this particular curve x0 plus y0 square by 3. Because if you make it square, so this will be y0 square by 3 to the power minus 2t, then if you add them, then you will be having this one. So now just try to understand what is the beauty of this problem. You are choosing your initial condition like this. So that means your initial point x0, y0 lies on this particular curve, correct? And accordingly, your solution trajectory is that curve itself, x plus y0 square by 3. And this is a parabola like this. So along which solution trajectory will be approaching to the origin, and rest of the trajectory they will looks like this one and this one, correct? And now try to understand then this and that particular phase portraits, they are topologically equivalent. So what is happening here, that this line remains horizontal and the vertical line, this is actually stretched in a way, it will be constructing this curve x0 plus y0 square by 3 equal to 0, and rest of the trajectory will be stretched accordingly in order to have this kind of structure. So if you consider a very small vicinity of the equilibrium point for this nonlinear system and this phase portrait, probably you can convince yourself that they are topologically equivalent. So in order to understand the stability behavior of this point, if both the eigenvalues are either non-zero or having non-zero real part, then the corresponding linear system will give you the nature of the solution trajectory nearby the equilibrium point. Last, I will just give you a simple idea of the global stability for a nonlinear system with a specific example, but of course in the next lectures I will be coming back to same system, because this is a simplified version of a well known single species population model. So this is a nonlinear system and I am considering this problem within the domain x greater than equal to 0, because I will explain you that how this is related with some population model, and in order to make an appropriate sense for this problem, so x happen to be positive. Now it has two equilibrium points, that is x1 star equal to 0 and x2 star is equal to 1, correct? F dot x for this problem will be equal to 1 minus 2x. So from linear stability analysis, at 0 this is positive, at 1 this is negative. So therefore x1 star equal to 0 is locally unstable and this is locally stable. Now the point is that we can prove that if we start from any point x greater than 0, then all the solution trajectory will be approaching towards this equilibrium point by constructing a Lyapunov function. So Lyapunov function means you need to construct a positive definite function which is positive definite except at the equilibrium point, and its time derivative should be negative definite except the equilibrium point. If this is satisfied, these two conditions are satisfied, then we can say that particular equilibrium point is globally asymptotically stable for the given system. So for this problem I can construct this V as x minus 1 minus ln x. So what is the general format for this kind of Lyapunov function? General format for this type of linear Lyapunov function is x minus x star minus x star ln x by x star, but you should keep in mind there is no unified way by which you can construct a Lyapunov function for the given system. It is rather some sort of trial and error method, but for this problem you can construct a Lyapunov function like this, and this is obtained from this structure by considering x star equal to 1. So first of all you can verify number 1, that is V1 this is equal to 0 and Vx is greater than 0 if x not equal to 1, and of course the condition x greater than 0 is satisfied. So that means within its domain, right? Similarly number 2, if you calculate dv dt, so dv dt this is equal to dv dx times dx dt. So this is equal to 1 minus 1 by x dx dt. So this is equal to x minus 1 by x into 1 minus x. So this is equal to minus 1 minus x whole square. Correct. Already I have mentioned x is greater than 0. And then again you can verify that these two conditions are satisfied, that is v dashed 1 this is equal to 0 and v dashed 1 this is negative definite for x not equal to 1 and of course for x greater than 0, because this function does not makes any sense in terms of real variable if x less than 0, because ln is present here. So therefore both the conditions, that means except the equilibrium point v is a positive definite function, and except at the equilibrium point the time derivative, that is v dot x, it should not be 1, v dot x is less than 0 for x not equal to 1. So therefore it is a negative definite except at the equilibrium point. So therefore this x equal to 1 is globally asymptotically stable for this system, right. But keep in mind that there is no unified way by which you can construct either this function or some other equivalent format or applicable format for a particular problem under consideration, but there are some trial and error method and there are some different new papers or some earlier works by various people and various group of people for population dynamics model. They have come up with different types of Lyapunov functions to prove the global stability, but the most challenging part is the construction of this kind of function. And when I will be considering the Lotka-Volterra model in two variable model, I will show you the extension of this version in order to prove that coexisting equilibrium point is globally asymptotically stable under certain parametric restriction, right. So for this lecture I can stop at here, and just one quick question if you have.
You have given that f of x is equal to 1 minus x square and with two local points.
Yes.
And one is comes towards the origin, one is away from origin. So if there is any bound, so in which point it will comes and which point it goes. And you are giving some small perturbation.
No, in that case actually that is some sort of nature that you are talking about this problem, that is x dot equal to x square minus 1, right. X dot equal to x square minus 1. Actually what will happen in this line, if you consider this is your x1 star equal to 1 and this is x2 star, this is equal to minus 1. So nature is this one for entire domain, that means minus infinity to plus infinity, because there is no other bound. But there might be some more bound if you change this functional format, because in this case what you are having two equilibrium. I can give you a very simple clue by which you can construct that one system having 3 equilibrium, one system having 4 equilibrium, and then you can change their stability property as per your own choice. How to construct that? That first of all, if you just consider this one, x into 1 minus x, you have 2 equilibrium, right. Then you can consider x dot is equal to x into 1 minus x. Either you can write x minus 2 or 2 minus x, right. So depending upon whether x minus 2 or 2 minus x, stability property of 0 and 1 will be changed, but you will be having one more equilibrium point x equal to 2 compared to this system, right. Similarly, this is nothing but your x plus 1 into x minus 1, and this stability property will be completely changed if you just introduce one x here. So that is x into x square minus 1. So if you consider x into x square minus 1, so you have 3 equilibrium point, that is 1, 0, minus 1, and if you keep on doing this, that is 1 minus x, x minus 2, 3 minus x, x minus 4, x minus 5 and so on. So you will be having 0, 1, 2, 3, 4, 5 as the equilibrium point, and the way you are introducing either it is x minus 2 or 2 minus x. So accordingly the sign of derivative evaluated at the respective equilibrium point will be changed due to the presence of additional term which have contribution from this kind of multiplicative factor, and accordingly the behavior may be changing, may not be changing, depending upon that how you are introducing this kind of new factor into the system. So in this case of course this trajectory is approaching to plus infinity. But this will not be the case. This will not be the case if you introduce one more equilibrium point here. Just for example, x square minus 1 into, you can introduce either 2 plus x or 2 minus x or x minus 2. So there is one more equilibrium. So if this equilibrium point is unstable, still it cannot cross x equal to 2, because x equal to 2 is a rest point, right?
So for any system, instead of going for eigenvalues, we can eigenvalues also give somewhat stability. That's some relationship also there.
Yes, yes, because that I have explained in the previous example, that was the geometry, and then you can just evaluate all those derivative at the concerned equilibrium point, and whether it is positive or negative, then you will be having these things. And when I will be considering 3 variable problem in case of population dynamics model, so then it will be quite difficult to find out the roots explicitly, but there is one criteria, that is called Routh-Hurwitz criteria, by which you can judge the stability by looking at the coefficient involved with the characteristic equation for 3 cross 3 matrix.
It involves some Gascoigne's algorithms like that.
That is actually somehow related with the eigenvalue problems, but for local stability analysis, the Routh-Hurwitz criteria is most general, because you can give a general condition for n cross n matrix, and depending upon your problem, whether it is n equal to 4 or n equal to 5 or n equal to 6, just looking at the coefficient of the characteristic equation, you can judge whether the equilibrium point is stable or not. Okay.
So that is for larger systems.
Yes, larger system. Okay, so I can stop at here.